Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, today's lecture is about particle swarm optimization, section 7.3. It is a continuation in the series of lecture 7, swarm intelligence, in the course of CS352 Introduction to Soft Computing. In section 7.1, we have basically already introduced what swarm intelligence is and what are the different operators of swarm intelligence, as well as giving you a brief overview of different algorithms of swarm intelligence. In section 7.2, we had basically discussed an algorithm for swarm intelligence which is called the ant colony optimization, which was based on the behavior of ants and how ant colonies operate when they have to move towards a food source. And in that regard, we had discussed the concept of pheromone and how a traveling salesperson problem can be solved using the ant colony optimization. In today's lecture, we'll be discussing another technique from the same swarm intelligence group of family of algorithms. And today's technique is going to be about particle swarm optimization, or PSO in short. After today's lecture, and in the next lecture, we'll basically be discussing the different applications and importance of swarm intelligence. In particular, we'll be focusing on the applications of particle swarm optimization and ant colony optimization, and we'll see the different problems that have been solved using these techniques. So let us formally start with section 7.3, swarm colony optimization. I must tell you that this is a really exciting and really intuitive algorithm that we're going to see, and you'll be amazed at how simple it is and how complex problems it can solve. More than that, it is exactly the simplest way to deal with an optimization problem, as you'll see. And you'll be amazed at, or you'll be asking me this question, I think definitely at the end, that why didn't we study this as our first algorithm? And I'll come to it maybe at the end of the lecture again. So let us start with discussing the agenda for section 7.3 before we finally start the actual contents. I'll be displaying an optimization problem, a specific problem in which we'll need to find an optimal solution. Then we'll see what techniques we have already studied and how they can be applied. In a very quick overview, it won't be too detailed, but it will just be a basic intuitive sense. Then we'll try to find the simplest intuitive solution that might come to your mind, and while discussing that intuitive solution, you'll kind of realize that the problem was really easy to solve if we had already used this technique earlier. This will then bring me to talk about introduction about the particle swarm optimization algorithm, or the PSO as it is called. We'll discuss the salient features of it and the basic working of PSO. I'll be giving you a very simplified overview of PSO, which will then be followed by the formal pseudocode and the algorithm of PSO, and that will bring us to the end of this lecture, and I'll summarize the whole topic for you. And this is the overall agenda that we have for section 7.3. So let us talk about a particular problem, a practical problem. There have been a lot of thefts going on in GIK Institute, and to stop those thefts, we would want a surveillance system. Two security personnel named Musa and Zakaria have been tasked to come up with the security system, and what they've identified is that they have they'll want to be stationed on top of the highest building in GIK Institute. For that purpose, you are given the map of GIK Institute below. For example, there are these different buildings that you can see here, and Musa and Zakaria want to find which of the buildings is the highest one so that they can be stationed on top of that building. Let us suppose, just for the sake of simplicity, that these buildings are all arranged in a single line. So you'll start from one building, on top of one building, and you can go on in that direction, or you can go forward in one direction, that is you can go from the first building to second building, and then from second to third, and so on. And the other way is that you can basically start from the end and move towards the first building. So these are the two directions that are possible. What Musa and Zakaria have are basically two important tools. One is that they can measure the height of the building on which they are standing, and secondly they can measure, of course they can also measure the height of the next building as well. So they can measure the current height and next height, and then they've got a communication tool so that Musa can communicate to Zakaria and Zakaria can communicate to Musa. So keeping these particular restrictions in mind, number one, the restriction is that you're going to only move in one direction. So if you want to move from left to right, you will be covering the first building, then the second building, then the third building, and so on. Or you can move from right to left, that is from the last building to second last building, and second last to third last building, and so on. So Musa and Zakaria are the two guys who are tasked to come up with the solution here. The problem is that they just want to find the highest building in JIK Institute. So if you were Musa and Zakaria, how would you find the solution that is the tallest building in this particular landscape? So first, I think you have to formalize this problem. Look at this problem deeply, what the problem is, try to classify it, and then you might be able to simplify it and find the proper solution or the algorithm that we can use to solve this. So if I simplify the problem from the real world problem to the model problem, the model here is that we have got a state space. The state space is, in this particular case, is 1D landscape, and in this 1D landscape you have to find, the problem is to find the tallest building or the global maxima, if you want to say the highest building. And the global maxima in this case would be the building that is tallest, and you want to explore the whole space. So there are multiple ways of solving it. If I think out loudly now, I'm trying to solve this simplified model instead of the real world problem, and the simplified model here is just a 1D space that is being explored. And the simplest way would be that, if we could somehow find the height of all the buildings. So if, for example, the height of all the buildings is given somewhere, someone has already measured it for us, and all we need to do, or Musa and Zakaria need to do, is that they need to go and find this tallest value. And once they have the tallest value, the highest building value, they can just simply go to the building and stand on top of it and look out for the security, and their job is done. They found the tallest building. But this solution, which I call the exhaustive solution, requires that we know the height of each building, that each building be measured, and only then can Musa and Zakaria work this out. And if this has already been done, perfectly fine. If not, we'll need to devise a strategy with which this has to work. So without looking at the exhaustive solution, that is one way, of course. And we know the problem there is that measuring each building would be exponentially, it would be too difficult or exponentially impossible to do. In particular, if you've got more dimensions, and in particular if you get more buildings. So if there are, for example, thousands or millions of buildings in JIK Institute, then it would be almost impossible for the exhaustive solution to work. So what other things can work? Thinking out loudly again, I would say this to me seems like an optimization problem where we have to find the optimal solution. The solution could be, if you don't want to search exhaustively in an uninformed manner or maybe informed manner using a heuristic, then the other way is that this can be viewed up as an optimization problem where you start from one end or start from a random position, and you move towards you take the best moves at that point and move towards the highest possible building from that particular point. You can have random starts, you can have multiple starts if you want, and finally come up with this one solution that gives you the most optimal value. So in other words, I have now transformed this problem from exhaustive search or informed or uninformed search to now an optimization search problem, where we start from a random points and actually move towards just take the better moves and keep on moving until we reach the local maxima. And if we have multiple starts, we'll kind of assume that ultimately we at some start we'll probably get to the global maxima. So in this particular case, we have avoided the problem of looking at all the buildings exhaustively, and we have kind of overstepped the complexity problem. And this particular algorithm that we've used here is called the local hill climbing or local maxima problem. And this hill climbing algorithm will actually give us kind of an optimal solution, which might be the best, but as we already know that we might get stuck in local maxima and local minima. In this particular case, we'll get stuck in local maxima, and that is the main problem with this algorithm. So is there anything else that we can do? Well, certainly yes. We already know that we can use simulated annealing and maybe make some bad moves. Or the other way could be that we could use genetic algorithms, as we've already seen, and in this case we'll need to have multiple possible solutions and randomly change them. We need to convert this into a binary problem, a bit string problem, and somehow we need to formalize it and come up with the proper solution. But as I see it, it's even in 1D, it's almost very hard to come up with the right formulation for genetic algorithm, which is kind of guaranteed to converge to the global maxima. And if we talk about the simulated annealing problem, it could work, definitely yes, but again I think it's at least in the simulated annealing one, we are not making use of two persons. Musa and Zakaria are two separate persons, and they can actually work in a better way, in a more efficient way to solve the problem really quickly. So in that regard, I must say that all the optimization problems that we have seen so far will not be very useful here. Of course, the way we have solved them might work. We might get to the global maxima, we might get to the highest building, provided that for genetic algorithms we have correctly modeled the whole system, and for simulated annealing we have set the parameters correctly enough so that it works. But as of now, it probably seems that even for a 1D problem as simple as finding the tallest building or the tallest point in a given landscape, those are not as efficient, or those are not making use of the multiple resources that might be possible. In simple words, in today's world, we have got computers that can work in parallel, and all those algorithms actually that we have seen are required to work in sequential order, and hence we are not making use of the parallel architectures and parallel working that can be done to explore a land, and that is something that is the drawback of those optimization algorithms. So that is a kind of a quick overview, must I say, that what we have studied so far on such problems and how they are being applied to this particular problem, and what are the drawbacks and the advantages of each of those. Okay, so we have decided that the previous optimization algorithms, since they are not making use of parallel resources, and we have got Musa and Zakaria, who are two different persons and resources, we want to make use of parallel resources. So what algorithms have we studied where we can use these parallel resources? The first thing that comes to my mind is the ant colony optimization algorithm. And while yes, it does make use of parallel resources and parallel persons, we can define a pheromone kind of a concept here as well. But the problem is with ant colony optimization, we need to start from a point and reach a particular point in map. The point, the goal is known, the starting position is known, and there are many paths that one would take to reach the goal. And those paths were important, and that was what we were trying to identify or optimize. In this case, that is not the scenario at all, because what you're worried about is the goal state itself, the optimized value itself, and not the path or the shortest path or something. So in that sense, this problem cannot be solved by the ant colony optimization algorithm as well. Having said that, there's a very interesting and very intuitive, simple way that I think each of you, or when you first study these kind of problems, that would have been the first solution that would have come to your mind. So why don't we do this, that spread Musa and Zakaria apart to the two edges or the two corners, and make them make them move towards each other, such that by the end of the whole iteration or run, the one who is at the highest point, at the peak, basically will be at the global maxima. So how does that work? Well, Musa and Zakaria in this particular case, since this is a 1D or a single line, put Musa at, let's say, at the start 0 point, and put Zakaria at the end point at, let's say, the nth building or point 1, if the total distance between all the buildings is 0 and 1. Let's put Zakaria at 1 and Musa at 0, and they both start moving towards, they both take one step at a time, and in each step they basically only move if they have information that the other guy is at a higher value, it has a higher peak than the previous one. So in this case, if you realize, we'll require specifically 2 or 3 particular tools. The first tool is that, and I think when I was defining this problem, I said that Zakaria and Musa had those tools. So let's go through them again. The first tool that Musa and Zakaria require is basically the communication with each other. So Musa can communicate to Zakaria the highest value that he has found, and Zakaria can communicate to Musa the highest value that he has found. So that is one thing, the communication is important. Number 2 is parallelism. So they're both searching at the same time, so they're searching in parallel. That reduces the search space, or that improves the efficiency of the algorithm quite a lot. And finally, they've got a tool with which they can measure the heights of the building. So the thing that they're going to communicate is they can know the height, the current height, and the height of the next building or something. So that is how this is going to work. So having said that, let's start this with this algorithm, and we'll see how this simple intuitive function is going to work. So in the first step, Musa is placed at the point 0, and he knows the height of his current building where he's standing. He is one solution. The other person, Zakaria, is on the other side of the spectrum at the other end, and he knows the height of the building he's currently standing on. So they both know the height of each other, and from here Musa realizes that while he's standing on a higher building than Zakaria, so the first thing is that we need to compare who's standing on the higher point, and the other guy has to move for sure. So in this case, we realize that Musa, who is at point 0, is standing at a higher building than Zakaria. So Zakaria has to move towards Musa, and what he does is they can both, of course, take only one step at a time. So Zakaria is going to take a single step and move towards the next building. And that's the first step, because he realizes, Zakaria realizes that Musa is at a higher point, so Zakaria has to move. At the same time, Musa also realizes that the next building, the building that's right next to him, is higher than his current standing. So he also has to move towards the next building, which is at a higher point than his current standing. If that is the case, then Musa also has to move. So the first move in this particular scenario, Zakaria moves because he knows that Musa is standing at a higher building than him. Musa also moves because he knows that the next building, which is his next step, is going to be higher than his current building. And Musa also knows that since he is higher than Zakaria, so he does not have to necessarily move towards Zakaria, but because the next building is higher, so he has to take the next move. Now in this current scenario, again, Zakaria notes that Musa is at a higher point than Zakaria, so Zakaria has to move towards Musa for sure. And at the same time, Musa realizes that Zakaria is at a lower point, so he does not have to move towards Zakaria. And Musa also realizes that the next building towards which he is going to move is at a lower point than his current building. So he is not going to take a move in this particular step, and only Zakaria will move further towards Musa, take another step and move towards the next building. Now there is an interesting scenario. Zakaria is now standing at a higher building than Musa. So what happens? In this particular scenario, Zakaria realizes that he is at a higher building, and not only is he at a higher building, but also the next building that he is currently standing on to, his neighboring building, is lower than his current building. So Zakaria will not take any move in this step, while Musa will move towards Zakaria now. And in this particular step, only Zakaria is the one who is going to move towards Zakaria, although Musa has the next step that Musa takes is going to be lower than his current one. In this particular scenario now, Musa realizes that he is at a lower point than Zakaria, and he still needs to take another move. While Zakaria is still stuck at his point, he knows that the next point or the point before both are lower than his current value, so he will not take any move. While Musa is going to take the move towards Zakaria because Zakaria is at a higher value than Musa. So if a person is at a higher value, he will always take that move. And that's the main scenario here. Although I might change my words a little bit, it's not as simple as just looking at the other person, but rather we'll be looking at two things at the same time: the next neighbor, the value of the next neighbor, and probably the value of the best person in all the swarm, or in all the parallel people that are present. So just for simplification, I'm going to say here that we're just looking at the next person. If he's at a better place, we'll just move towards him. Although that's not really true, and as we'll see when the actual algorithm gets explained, that it's not just one factor, but it's going to be three different factors that are going to be taken into account. But for now, what is clear is Musa has got a peak right next to him, so he'll need to take that move for sure. And also, since Zakaria is at a higher point than Musa, so Musa will take the move towards him as well. So it's the same move, but it's justified. So now let's take the next scenario, and what we see here is that Musa is now at the highest point, Zakaria is now at a lower point, and again this time Zakaria will have to take the next move, which is towards a lower value. And since he realizes that Musa is kind of at a higher point as well as so in this case Zakaria is going to take the next move and move towards Musa. Again, I must warn you that in the real form we'll see that this might not happen. Depends on the scenario and depends on the difference between the best value and the next value that Zakaria has to make, but let's keep things simple, and Zakaria will only move if, or Musa will only move if Zakaria is at a higher point than Musa currently. So in this case, Zakaria will move towards Musa. Again, it's the same scenario that gets repeated. Musa is at a higher point, Zakaria is at a lower point, so Zakaria will move towards Musa, and already Zakaria also realizes that his next move is going to be better than his current move. So he'll move towards Musa and take the next move here. The scenario will again continue. Zakaria realizes that Musa is at a higher point, so Zakaria will move towards Musa, and Musa will stay at his current place. The same step can still be seen here, and finally I think it would be that in this particular case Zakaria again realizes that Musa is at a higher point, so Zakaria will move towards Musa and reach him actually in this particular step, while Musa will stay at his peak or at his point. Finally, both Musa and Zakaria have met at the peak, and at this point we can see that there is no further move possible as they are both at the same point, and the left and right of both the persons is at a lower value than their current position. So the building on which they are currently standing is probably the building that is the highest in this whole landscape in GIK Institute, and from here they can have a look at the whole overall security situation of GIK, and hence this is the solution to the current problem. So a couple of things that you might have noticed while I was discussing this was that we made use of parallel resources here. I think that's so we had multiple solutions at the same time. That is mainly the difference between the current algorithm or currently proposed solution and the solution that got proposed in different optimization problems. And that's the first thing. The second thing is the only algorithm that comes somewhat closer to our solution was the genetic algorithm, where also there were multiple solutions. But what you notice is that in those solutions or in those particular problems, the solutions were either retained or were basically removed completely from the whole population, and there was a systematic formulation and solution, but there was a lot of randomness that was involved. In this particular problem, the way we have solved it, there is not too much of a randomization. Actually, there's almost no randomization, but we'll see when we develop the mathematical notations that there is a bit of a movement issue or a randomization issue, but when that will come, I'll discuss that. At the moment, what we can see is that there are some similarities in terms of the number of solutions that are retained with genetic algorithms, but at the same time, the mathematical foundation or the way we looked at, coming up with a crossover and evolution and genetic values, that was the thing that we have kind of not done in this particular scenario. Keeping that in mind, I must say that you must look at the salient features of this particular problem, which is basically working in parallel, number one. Number two, having information or communicating with your all the other agents or all the other persons that are present in the swarm, and trying to solve it using information gained from them as well as having your own information given to them. So this brings us to the algorithm formally. The particle swarm optimization or PSO is an intelligent optimization algorithm. It belongs to a class of optimization algorithms called meta-heuristics. PSO is based on the paradigm of swarm intelligence, and it is inspired by social behavior of animals like fish and birds. PSO is a simple yet powerful optimization algorithm, and it is successfully applied to enormous applications in various fields of science and engineering. For example, machine learning, image processing, data mining, operational research, and many other fields. Initially, PSO was introduced by James Kennedy and Russell C. Eberhard in 1995. Originally, they were working to develop a model to describe the social behavior of animals like flock of birds and school of fish. However, they realized that their model is capable of doing optimization tests. So, they proposed a new optimizer based on their model, which is called particle swarm optimization. An image of the original paper is shown here, which is entitled A New Optimizer Using Particle Swarm Theory. In the last 25 years since 1995, the introduction of PSO, the PSO became one of the most useful and most popular algorithms to solve various optimization problems in various fields. One of the key points behind the PSO is its simplicity. PSO is a very simple algorithm, as we have seen in the example. However, it is a powerful algorithm too and comes up with solutions for most of the problems in a parallel environment. PSO is very similar to the search mechanism that Musa and Zakaria used. In the structure of this cooperation between them, two principles are used. These two principles are communication, which is informing the Mayyad height to the other party, plus learning when Zakaria moves towards Musa or Musa moves towards Zakaria. They actually learn that location of the other party is better. Learning the concept of better is the main problem that an optimizer should solve. When an optimizer learns the concept of better, it is able to solve any kind of optimization problem, because the solution of optimization problem is to find the best one. So, if we know what is the better, we actually can discover the concept of best. In this simple story, cooperation of Musa and Zakaria to find the global maximum of a one-dimensional function, we simply discussed about the basic rules behind the swarm intelligence. Musa and Zakaria don't know about the global maximum of the problem. However, via cooperation, they are able to find the answer, and the swarm intelligence is something very similar to this. In swarm intelligence, an intelligent behavior is created by means of some agents like birds, like ants, like fish, and this level of intelligence is absolutely unreachable for any member of the swarm. But with cooperation among the members of swarm, among the members of colony, this level of intelligence can be reached. And this is the concept, the paradigm of swarm intelligence. PSO is a swarm intelligence method, and its users are some unintelligent agents called particles to reach an upper level of intelligence, which is absolutely unreachable for any of the particles in the swarm individually. So let us start with particle swarm optimization, and let us start with a very simplified implementation. We'll take a couple of examples and we'll see how the swarm optimization actually works. You'll need to keep in mind a few things from the previous example. First and foremost thing is that I would like to say that the example that I took of Musa and Zakaria was really simplified. In real life, most cases are not as simple. Even the simplest case would be a little harder and a little let's say more complex than the very simplified case that we had taken. So What are the specifics of particle swarm optimization? With the previous thing in mind, you need to just realize that particle swarm optimization, the world consists of three main things. One is a particle, the other is a swarm, and the third thing is optimization. The particle itself, if I have to say it, is basically an agent or a person or a particle. It will have some particular characteristics, like it will have a position, its current location, and basically a velocity, a direction in which it is moving or it has to move to get the new position or the next position. So it will have two characteristics associated with it, a position and a velocity. Since we have another word called swarm in it, swarm will actually mean that it is basically a community, a group, a couple of agents that are working together to reach a particular goal. And since it's an optimization problem, we don't know the goal. Like I said before when I was defining optimization in lecture 5, I guess. So we don't know the goal itself, but what we do know is that we want to optimize from the current position, and hence this becomes a particle swarm optimization algorithm. The particles can change their position by adjusting their velocity. Of course, the velocity will keep on changing, and if the velocity changes, then automatically the next position will also change. And the reason for changing the velocity might be different for different systems. For example, the flocks of bird adjust their velocity and direction to seek food. For example, as we have seen in fishes, the school of fishes may change their direction and velocity to avoid larger fishes and larger predators, or simply, as we'll probably see in the next slides, it might be used to identify optimized environmental parameters. The thing to note is that each particle will memorize the best location identified by it, which we call the personal best of each particle. The particles will communicate the information regarding the best location explored by them. So this will be the global best location. And how will we modify the velocity of the particle? Well, the velocity of the particles will be modified by using the individual experience of the particle as well as using the best experience of the group, that is the global maxima as well as the local maxima or the local information available to the particle as well. So with these things in mind, we'll now move on towards the basics and determine the equation for particle swarm optimization. Okay, so now we are going to discuss the equation and the simplified version of PSO, the basics and the concepts behind PSO. So the first thing is that, as I said, there are multiple particles that are participating. So let us suppose that there are n particles. In the n particles, each particle will be denoted by basically ith, will be called ith particle. So if you see the equations here, I'll just introduce the equation first and then I'll go on to the each individual index and stuff. So what you're seeing here is that, like I said, each individual particle has a position and a velocity. The position of a particle is represented by xi, I for the ith particle and x as the position. And if you want to add time to it as well, for example, in the tth iteration for particle I, the position will be represented by xi comma t. So for example, in the t plus 1 iteration, it will be represented by xi comma t plus 1 for the ith particle. So the position of a particle is represented by xi. The particle velocity is represented by v, and in particular for an ith particle it will be vi. And here it would be really simple to say that the overall experiment will consist of just these two equations, and on each step you'll have to find the next position of the particle. To find the next position of the particle, you will require basically the particle velocity at that particular point, and this is how you determine the position of a particle. The position of a particle is in the current move is determined by basically xi comma t. This is equal to xi comma t plus 1, and this is equal to xi, which is the comma t, which is the previous position, plus vi comma t plus 1, which is the current velocity. So to determine the position, you will need the previous position and the current velocity. And if we talk about the particle velocity here, since it's vi t plus 1, so for each individual particle it will have its own position and its own velocity. The particle velocity is determined by this equation, where it is vi is equal to wvi, and you'll notice that there are three terms and I'll come to them in a minute, but at the moment you just need to remember that it's wvi plus c1 r1 multiplied by p best for I minus the current position xi plus c2 r2 multiplied by the global best minus the current position. So in this particular case I have introduced a few variables, and I like to give them brief you about these variables. Vi here represents the velocity of the ith particle. W is the inertia of the particle, that is how much do you want them to remain in the current position only. So for this case, it's kind of a weight that you can give to the current position. Then you have got two variables called C1 and C2, which we call the acceleration coefficients. So these are supposed to be coefficients that give weight to the personal best and the global best, and they're kind of the weightage coefficients again. But as W was inertia that was giving weight to the current position, these two are the coefficients for change and how quickly do you want to change your position. That is done by the acceleration coefficients C1 and C2. Then you have got two random numbers R1 and R2. They have to be between 0 and 1 specifically, and they are also kind of giving weightage to the solutions and the change in solution. So and their size, I must say, is 1 cross D. They are basically one-dimensional vectors, and they have got D values. The capital D here is the number of variables or the dimensions of our solution. So for example, if you need a 2D solution, then you'll have two dimensions, and each random number here is going to be a 2D vector consisting of two numbers, 1 cross 2. And similarly, if you have a 3D vector or a 4D vector, these dimensions will change automatically according to that. So for example, if you have got 4 variables for which you are finding solution, the size of the random numbers vector would be 1 cross 4 for C1 and C2 both. Then you have got another concept of P best comma I. P best comma I is basically the personal best for the ith particle, and then you have got another concept of G best, which is the global best for the ith particle or the whole system. I must say it will always be the same for all the particles that are taking part. So you don't see the index I over here as such. Then finally you have got the concept of xi. Xi, as I said before, is basically the position of the ith particle. What we have to do is that we have to evaluate the objective function fi and update the population irrespective of the fitness. So what you need to remember is that after each run, after each iteration, the objective function fi will be used to evaluate the solution, and the population will be updated regardless of the fitness. So this is one difference between the genetic algorithm and the PSO. In genetic algorithms, we would kind of reject the ones that had lower fitness value, or even in hill climbing, for example, you never take the move with the lower fitness value. But in this case, even if the solution is bad, even if the next step is bad, you'll have to take the next move, you'll have to update the population regardless. However, there are two things that will never change, or that will not change if the solution is suboptimal. So if your current solution is better than your previous solution, then you will update both your p-best and your g-best. So p-best is just a local information. If your local best is better than the previous local best, then you change your current local best to the newer value, to the hypothesized value. But if your current p-best, your current local experience is not better than your previous p-best value, then you will never change them. And the objective function fi will actually help you evaluate your p-best and help you compare your previous p-best and your current p-best. That is all that is mentioned in this particular equation. In the second part, of course, you want to compare g-best, and the same rule applies as well. So if your personal best now is better than the global best, you will update the global best. But if your personal best is not better than the global best, then you simply don't update the global best at all. So to summarize, in each iteration, your position will definitely change. The position of a particle will be modified for sure, but the personal best and the global best will be conditionally modified based on certain conditions. So now that you have seen how the equation works overall for particle swarm optimization, I'll just go in depth a little bit of the particle velocity and the three components, and talk about how each component is important in its own right. So if I again go back to the equation for particle velocity Vi, what you see here is that there are three components. One is Wvi, which I'll call as momentum part. The second component is the C1R1 multiplied by P best I minus Xi, which I'll call the cognitive part. And the third one is basically C2R2 into G best minus Xi, which is the social part. So talking about each of these parts separately, it is important to understand what these parts are and why they are important. So this is the conceptual part behind particle swarm optimization, and I might ask you questions from this part in your final exam, in other places, in your assignments, and maybe in quizzes as well. So pay a lot of attention to this particular part. Wvi, the first part of the equation, which is the momentum part, serves as a memory of the previous flight. That is it serves as a memory of the particle. It serves as the weight that you want to assign to the previous velocity, previous direction. It prevents the particle from drastically changing the direction. The other two parts, the cognitive part and the social part, are basically there for changing the direction. And the more weight you have to the current velocity, of course, to the inertia W, I think the more it will prevent the particle from changing direction drastically. In that regard, the value of W is very important here. Since Vi will be changing continuously, but W is a constant that you choose, and that the value of constant is very important for determining the behavior of particle swarm optimization. Another way of looking at WVI term is basically, or the momentum part is, that we can think of it as a bias towards the previous direction. So how much important is the previous direction? The WVI dictates that part. So that is why it is called the momentum, and changing in momentum is very hard to achieve. WVI assures that the previous velocity does have a lot of say in current velocity depending on the value of W. Okay, then we move to the second part, which is the cognitive part. The cognitive part is basically C1 R1 multiplied by the personal best for ith particle minus the previous position of ith particle. This term is called the cognitive part, and it quantifies the performance of ith particle relative to its own past performance. So now we have got the local information, and we want to compare the performance of current particle, the current position of the particle I, with the best position of the particle I, and hence we are quantifying it locally relative to its past performance. Particles are drawn back to their own best position, so we are trying to pull each particle towards their own best position, and this is the change in direction that is going to be suggested. We can view it as nostalgia of the particle, that is the memory of the particle that it wants to go back to its own best. It has observed something and it wants to move towards its own best. So that this is the nostalgia of the particle, and this was one part that I had said was missing in the Musa and Zakaria example. So in the Musa and Zakaria example, we didn't talk about momentum and cognitive part as such, but we just talked about the social part, which was dragging the person with lesser memory, with lower value, with the building that was at lower height to the higher one. So they only contain the social part in there. So what is social part? Social part is basically C2 R2 multiplied by the global best minus the current position. It quantifies the performance of ith particle relative to all the other particles in the swarm, and in that sense it's kind of a global phenomena. It's pulling all the particles towards a single best position that is determined for all the particles in the swarm. The particles are drawn towards the best position determined by the group, so it's a group decision, and for the whole group the best position has been determined and particles are continuously pulled towards it. It resembles the group norm that each particle seeks to attain. So it's kind of like asking each particle that, as a group we have found this as the best position, you should all come up and pull yourself towards this particular person or this particular position. So with this, I think everyone should be clear about the three terms that exist in the particle velocity and the role of each term as well. The first term is the momentum part, whose role is to keep the inertia intact and keep pulling towards the previous position. The second part is the cognitive part, whose role is to serve as the memory of the particle and pull each particle towards the personal best of that particle alone. And this is necessary because each particle will also have a personal memory, a cognitive part, a personal space, and it will have a nostalgia where it will want to move towards. So the cognitive part assures that this thing happens. The final part is of course the social part, which is the global memory of the system and how the overall system should behave. So the social part pulls towards that, and we'll see in later examples. Maybe I'll give a small demo as well in the next slide, where I'll talk about how these three terms are added up and how this movement actually happens. The best example that I can give for explaining all of these three vectors or these three components of the velocity vector and the position is by the graphical representation. So here what you're seeing is a particle or a person whose current direction is given by the orange arrow. His personal best location is given by the red arrow, and the team's best location is given by the blue arrow. And I think the vector here, the vector representation is very helpful in understanding the concept of how the velocity is changing and what are the components and the effects of each component in the overall equation. So the current position where the person or the particle is currently standing is xi, that's his current position, and his next position basically will be determined by basically a sum of the vector of current direction, personal best location, and the team's best location. The contribution from all these will be taken, summed up together, and added to the current position to determine the next direction. And we'll just do that in the next slide. So in this slide, you observe that there are three different vectors, each contributing some part to the final position. The first vector, which is colored in yellow, is the momentum part, and what you see here is that there is a small contribution from the momentum part towards the final goal, which is shown here in green. Then there is another contribution from the personal best location. Again, we add the contribution to the vector, and finally we have got some contribution from the team's best location, which is also added as a separate vector. So once you add these three vectors, you get the final solution, the green solution, which starts from the current position and ends at the final position to give you the next position or the new position of the particle. And this is done for each particle and in each iteration to generate the next position of each particle in each iteration. Ultimately, this will help you reach the goal state or the state at which the swarm is going to converge. So the particle swarm optimization algorithm runs in iterations. In each iteration, there are two parts that you need to understand completely. First part is the generation part, and the second part is the update part. In the generation part, as we have seen, you basically generate the velocity vector and you use it to update the position. So that is the generation part. The next part after generation is the update part, in which you need to update whether your personal best is better than or worse than your current solution, as well as you need to update the global best if it is better than or worse than the current solution. So we have already seen in the previous slide how the generation part works, and we have seen how the velocity is generated and the effect of each component of the velocity vector. But now we need to see how the update part works, and in the update part there are basically four different cases that are important to discuss. The update part is only concerned with the comparison of the current solution with the personal best and with the global best. So for example, in this scenario there are two variables that are possible, and hence we have got four different scenarios that can happen. The first scenario, called case 1 here, is that your proposed solution, your next solution, is neither better than the personal best nor better than the case 1. What you see here is that you have got, suppose, a vector called x, which has got values of 5 and 6, and you are trying to minimize the values here. This is a minimization problem, and after you put it in the function, it evaluates it to 61. So and you go back and look at your personal best. Your personal best is at 4, 5, which has a functional value of 41, and your global best has a functional value of 2, 3, which has a global best functional value of 13 if you evaluate it using function. So in this particular scenario, what you see is that your value f, which is 61, is larger than 41, and it is also larger than 13. So the f is larger than f of p best, and f is also larger than g best. Hence, your newly proposed value is worse than both the f p best and f g best. the newly proposed x, which is 5 6, is neither better than the personal best nor better than the G best. So this is case 1. What do we do in this case? In this case, we will not update anything, neither the personal best nor the G best. Simply let it be. In the second case, we observe that OR F value for the proposed position is better than the P best, but it is not better than the global best. So in this case, we'll simply update the P best value, but will not change the G best addition function. Let x be 4 and 3, and if we evaluate it using the function, the F value will be 25. So in this case, P best will be again 4 5 with the value of 41, and the global best will be 2 3, which is 13. So if you compare 25 with 41 and 13, we observe that the F now is less than the personal best. It is less than 41, but it still is higher than the global best, which is 13. So now we know that F, the current position x is equal to 4 3 is better than the P best of 4 5, but it is not better than the G best of 2 3. So simply in this case, we'll update the P best value to 4 3, so that it becomes 25, but the global best will not be changed and will remain to be 2 3 and functional value of 13. The third case that can occur here is if your new position is and the functional evaluation of it is better than the personal best, as well as it is also better than the global best. In that case, we want to update both the personal best and the global best in this iteration. As an example, let x be having a value of 1 3, and if you evaluate it using the function, it will give you a value of 10. The personal best in this case was 4 5 with a F value of 41, and the G best in this case was 2 3 with the F value of 13. So now we observe that 10 is both less than 13 as well as less than 41. Hence, the global position now should be x is equal to 1 3, as well as the personal best of the particle will also be adjusted to the personal best of 1 3. Hence now we have got the P best value of 1 3 as well as the G best value of 1 3 after this particle has been executed in this iteration. Of course, there is a fourth scenario as well, in which the proposed solution is better than the personal best. Sorry, the proposed solution is neither better than is not better than the personal best, but it is better than the global best. But unfortunately, this case cannot happen, since global best is by default always better than the personal best, better than or equal to the personal best. Hence this case cannot happen, and we do not need to update either the P best or the G best value in this case, and this case will never occur in a real number scenario. So we can kind of let this scenario go. In the last slide, I talked about how the update mechanism occurs, and before that I also talked about how the generation mechanism occurs. So let us now take both the scenarios and apply it to a real case and see how the variables will behave and how the algorithm itself will be ran. Please note that the number of iterations that I am going to mention here are going to be 10, but I'll just run it for 5 iterations and show you the result for 5 iterations. How do you run the particle swarm optimization algorithm on a real example? The case or the problem here is we want to find the minimum of the function x, which is basically sum of 4 variables. The 4 variables can have sum of square of 4 variables. The 4 variables can have possible values between 0 and 10 inclusive, and hence we have got 4 decision variables: x1, x2, x3 and x4. Each of them, of course, we know that the lowest possible value for function x would be 0 when all of these x1, x2, x3 and x4 are 0. The allowed limit or the allowed boundaries for each of these x variables is between 0 and 10. With that in mind, we start the first iteration and the generation step in the first iteration. Each iteration will consist of a generation and an update step. In the generation step, we'll generate values for the position, and in the update step, we'll update the personal best and the global best if needed. So in the generate step, what we need to do is, first of all, in the 0th iteration or in the first iteration, we fix the population size, we fix the inertia variable, we fix the acceleration coefficients, we fix the maximum number of iterations that are possible. So the population size NP is 5. So we have got 5 members in the population in each iteration. We have got the inertia set to 0.7. So this is the weight that is going to be assigned to the previous velocity. We have got the acceleration coefficients set at both set at 1.5, and finally we'll have the maximum number of iterations capital T set at 10. In the second step, we'll generate random positions within the domain and then evaluate the fitness as well. So the initial population is generated using random numbers and random positions. These positions have to be between 0 and 10. So for example, the value of x1 in the first member of the population is 4, x2 is 0, x3 is 0, x4 is 8, and if you just fill it in the fitness function, which is the sum of squares of these values, you will get 4 square plus 0 square plus 0 square plus 8 square, which is 16 plus 0 plus 0 plus 64, which comes out to be 80, as shown as the fitness value of the first member of the population. Similarly, the second member randomly generated is 3197, and if you take squares of each of them and add them up, the fitness value for the second member of the population is 140. Similarly, for the third one, the fitness value is 35. For the fourth one, it's 102, and for the fifth one, it's 113. So this is the initial population and your initial positions for the population as well as the fitness values of the population. Since this is the first iteration and we do not have any previous velocity set out at all, we'll start with generating random velocities that are within the domain of the variables. Again, this is represented by vector v, and it will have values between 0 and 10 for each variable. And as you can see here, so for example, for the first population, the random velocity is 9618. For the second one, it's 5130, and so on. So in step 3, we'll generate random velocities. So the number of solutions or the number of particles that exist in our population are 5, and for each of these we need to find their personal best. In the first iteration, the personal best is the same as the original vector values that were generated. So for example, the first vector value for the first particle was 4008, and we evaluated that it had a fitness value of 80. So the first personal best or the P best for the after the first iteration for the first particle would be 4008. Similarly, we can determine its fitness value, which will be called FP best from this point on. Similarly, you can kind of come up with the P best for the second particle, for the third particle, fourth particle, and fifth particle, and find their F functions as well. Similarly, we can determine the global best by taking the best function, which has the best fitness value. In this case, since we are minimizing the problem, so we'll take up the particle which has got the minimum FP best value. In this case, if you compare the 5 values, 35 is the lowest value, and hence 0315 is the global best of all the particles. Note that the global best here is the same as that of particle 3, the personal best of particle 3. What we have done so far is set out the inertia variable, the acceleration constants, and the number of iterations. Now we need to generate two sets of random vectors for this particular run. So let's suppose that we generate R1 and R2. Note that this is going to be a 1 cross 4 vector. Since there are 4 variables, this will be a 1D vector array. And in this case, we see that the values of R1 is 0.4, 0.3, 0.9 and 0.5. They have to be between 0 and 1. Similarly for R2, the values are 0.8, 0.2, 0.7 and 0.4. These are randomly generated vectors. Then in the next step, we can now determine the velocity of the particles. For example, for the first particle, the current velocity v1 is 9618. We'll use that to generate the new velocity, and the new velocity is v1 is equal to, and we can use the equation vi is equal to wvi plus c1 r1 multiplied by p best I minus xi plus c2 r2 into g best minus xi, if you remember. And from that we'll then use the velocity determinant to determine the new position. To determine the velocity, we'll just place in the values of all these vectors and parameters into the equation vi, and then the result that comes out after you put in all the values, we know the value of vi, we know the value of xi, which is the original position 4008. We have generated a random velocity vector of 9618. We also know its value, and we know the personal best, and we know the global best as well, 4008 and 0315. And we'll just fill in these values into the equation, and this gives us the value, the new velocity vector as for particle 1 as 1.5, 5.1, 1.75 and 3.8. So this is the new velocity vector. Now we can just fill in the v1 value into the equation to determine the new position, which is x1, which is 4008, which is the older position. You add to it 1.5, 5.1, 1.75 and 3.8, and the new values are 5.5, 5.1, 1.75 and 11.8. So it is important to note here that sometimes in certain cases it might occur that from a given position, when you add the velocity to it, it might exceed the allowed limits or allowed bounds. So of course, for example, if you are in a square and you have to remain within that square, if your value, if the square is, let's say, starting at position 0 0 and it's going up in 1 1, then you cannot reach coordinates, then the position possibly cannot go to coordinates like, let's say, 2 2 or 1 2 or outside 1 1. So it's basically 0 0 and 1 1. It's a square, so it's maximum going to be 0 1 or 1 0 or 1 1. Just it will lie in that plane. It cannot exceed those values. What happens if it exceeds those values? The excess can happen in two manners. The first thing, of course, and the first easiest scenario would be that you are within the bounds, you're within your line, you're on the line, or you're within the area specified. So you're within the square of 0 0 and 1 1, 0 0 0 1 1 0 and 1 1. You're within that square, and in this particular case, no bounding is required, nothing is required. Your solution is, your new position, I must say, is kind of correct and is within the bounds. But what happens when you exceed the bound on the upper limit? So for example, your upper bound was 1 1, but you now go to 1 2, or for example 0 2. So you have exceeded the upper bound on the y-axis, which is supposed to be 1 at max. In this case, you can adjust and you can bound your solution back to the upper limit, which is going to be 0 1. So if your solution was 0 2, then you can simply bound it back to 0 1, and now it is within the bounds, and the solution is now correct again. Similarly, another case that can occur is if you violate the lower bound in your new solution, and in that case what you need to do is you need to add in or shift the new solution to the lower bound. For example, if your solution is -1 and 1, for example, then in this case you have violated the lower bound on the x-axis, which has to be between 0 and 1, as this is a square. So in this case I'll move it from -1, 1 to 0 and 1. So that's how the bounded solutions can be achieved and the bound cannot be violated. So now we need to check for the bounds as well. Once you generate your new position vector, the position cannot possibly violate the bounds, as we already said that each position or each vector, each variable and each parameter would have a value of between 0 and 1, 0 and 10 inclusive. So in this case 11.8, which is occurring at the position 4, is violating the bounds. As mentioned in the previous slide, we'll bound it, and by binding it to the upper limit, since it is violating the upper bound, we'll bound it to the upper limit, which is 10, and hence the new position vector is going to be x1 is equal to 5.5, 5.1, 1.75 and 10. We can now evaluate its fitness function, which comes out to be 159.32, and finally we can update the population and replace the first vector by this new value. Similarly, in the iteration, we'll update all the corresponding values of every single member of the population, and hence we'll kind of update all the members in each iteration. What you can observe is that the fitness value of the first member was previously 80, and now it has deteriorated or gone bad to 159.32. Since it is a minimization problem, so we have actually gotten a worse solution than the original solution. But we'll see that despite making poor decisions at the start, ultimately the system should converge to the global optima, and this is because of the collective wisdom that is obtained in this scenario. So after the generation part, we'll now start with the update part. In the update part, we usually update the p-best and the g-best only, keeping in mind that the p-best had a previous value of 80, that was the previous memory, and the new solution has a fitness value of 159.32. Hence the new solution will not change the previous best behavior or the best values observed, which is 4008, and there is going to be no update of p-best1 in the current iteration. In the next step, we need to check for g-best. The global best was 35, which was lower than the p-best. If the p-best is not going to change, automatically the g-best will never change, and hence the g-best will also not be updated in the current iteration for particle 1. For particle 2, we'll need to repeat the same process that we repeated in for particle 1 in iteration 1. What we do have now is we have the random velocity vector v2, which is 5130. We have got the current position of the particle 2, which is x2, which is 3197, and it has a fitness value of 140. We have the personal best history of particle 2, which is 3197 itself, which is again 140 fitness. And finally we have the global best value of 0315, which has the global best fitness value of 35. So now what we need to do is, we are still in iteration 1, but this is doing the run for particle 2. We generate two sets of random vectors, r1 and r2, again with values between 0 and 1 for both. The vectors are of size 1 cross 4, since there are 4 variables. We then determine the new velocity, basically by multiplying the inertia values with the previous velocity vector, and using the different variables and values of parameters to generate the v2 value. We'll add the v2 value into the previous position of 3197 to generate the new position x2, which is in this case comes out to be 3.35, 3.2, 1.5 and 6.4, and we're just placing in the different parameters in the equation to get the new position and the new velocity vector for particle 2 in iteration 1. So now, after we've done the generation part, we need to update the values. The first step is of course checking for the bounds, and since they are not being violated in this particular step for particle 2, we'll move on and check evaluate the fitness function. The fitness function for the second particle is 64.67, which is better than the previous fitness value of 140. So in the first step we'll update the population by updating the individual population member as well as its fitness value. Then we'll update the p best as well, since the new solution is better than the previous solution. And finally, we'll not update the global best because the current value is not better than the global best, so it will not change the global best at all. With that, the required iteration for particle 2 is done, and we can now move on to the particle 3 and perform iteration 1 for particle 3 again. What we did for particle 1 and 2, we'll do it again for particle 3. The first step is as usual generation. In generation step, we'll generate two sets of random vectors. We already know the value of w, c1, c2, t, the velocity vector v3. We know the previous position x3. We know its fitness value is 35. We have the personal best already, and we have the global best as well, which is the same thing for particle 3. We then determine the new velocity by just filling in the values, and we finally determine the position by adding both the vectors. Basically by adding the previous vector, which was 0315, with the new velocity vector 4.9, 2.8, 0.7 and 2.8, and this gives us the new position as 4.9, 5.8, 1.7, 7.8. So we're done with the generation part. We'll check for bounds and then we'll move on to the update part. In the update part, first we'll check for bounds if the bounds are not violated. In this case, they are not violated, so we are not going to be worried about that. We'll then evaluate the function value, the fitness of the function, which is going to be much worse than the original function, which was 35. Now it has gone down to 121.38. We'll update the population anyway, regardless of the poorness of the solution, which is now going to be 4.9, 5.8, 1.7 and 7.8 in the third row of the population vector, and the fitness value will also be updated accordingly. However, neither the G best nor the P best will be updated in this iteration, since the current solution is way worse than the personal best as well as the global best of the current particle. We'll repeat the process that we have done for particle 1 and 2 and 3 for particle 4 as well, with two steps. The first is the generation step and second is the update step. In the generation step, we first generate two set of random vectors of size 4 cross 1 cross 4, and then after generating the vectors, we have got all the variables set, we've got all the parameters set. We'll determine the velocity, which in this case comes out to be minus 0.3, 0.3, minus 1.75 and minus 4.7. We'll then determine the position by adding the velocity vector into the current position vector, and this is going to give us some new values, which are 1.7, 1.3, 2.25 and 4.3. We'll then check for bounds and then we'll go for the update step. So in the update step for particle 4 in iteration 1, what we need to do is we first check for bounds. Yes, all the 4 variables are in bounds, so we don't need to change anything. We'll then evaluate the fitness of the value of the F4, which comes out to be 28.13, which is way better than the current fitness value of 102, and hence for particle 4 the values will be updated, and the P best as well as the global best will also be updated, since the the current best of or position is better than the global best. So the global best and P best will both be updated to 1.7, 1.3, 2.25 and 4.3. We'll repeat the same process for our fifth particle as well. We'll use the generate and update steps. In the generate step, two random sets of vectors are generated. We'll then already know the different variables and parameters now, so we'll just determine the velocity by filling in the values for Vi, and this comes out to be V5 comes out to be minus 2.52, 4.09, 3.87 and 6.26. We'll add it to the current position vector, and this is going to help generate the new position vector, which is 3.48, 6.09, 11.87, 9.26. Then we are going to check for bounds, and after checking for bounds, then we are going to go for the update step. So now in the first iteration we'll move to the update step for particle 5. Before moving to the update step, we need to check for bounds, whether the bounds are violated. In this case, we observed that in the newly generated vector, position vector, the bounds are indeed violated. For x3, which is 11.87, it should not exceed 10, so we'll bring it in bounds and set it to 10. That's the first step. Then we're going to evaluate the fitness of this new function, which comes out to be 234.95, which is way worse than the original fitness value of 113, and it is probably the worst in all the 5 updated particles. We'll then, however, update the particle population, the particle in the population P5, and it will be updated. And then, since its fitness is really worse, neither the P best nor the G best will be updated at all. And this brings actually an end to the iteration 1. Here all 5 particles have been updated, and after this particular iteration we'll be repeating these steps throughout. So now we have got the V vector set, we have now got the P vector set, and these values can be used to generate the next set of values, and we keep on updating the P best and G best until either we run out of iterations or a certain criteria has been reached, whatever the termination criteria has been set by the user. So here is a complete overview or review of what happened after we have completed iteration 1. The original P vector, the position vector that we had set, was 4008, 3197, 0315, 2149, 6283. The fitness values were determined for them. The P best were set as the same values, and then we have got the F function was also the same values as the original F function. The velocity vectors were determined randomly: 9618, 5130, 7414, 3021 and 1687. And from this we actually got the G best and F G best values as 0315 and 35, which was the third particle. After completing the first iteration, the values of P vector are all changed. The values of F vector are all changed. The P best might be changed depending on if the newer values were less than or better than the personal best values. And for other vectors, if it was not better, then of course they have not been changed. The same goes for the F function. And finally, the new V function that is generated after running this first iteration is also saved. So we now have got a new v vector, a new velocity function or v values, and after this whole run we have got the g best and the f of g best as well, which is basically the uh, fourth particle value here, as you can see. So this is after we have completed the first iteration. This is the results that we have, and similarly we need to run it for iteration 2 and iteration 3 and iteration 4 and 5 until we reach the termination criteria of 10 iterations, or if there is any other termination criteria set by the user, that has to be met after this run. Please note that each of the particle here is a solution in itself, just like it was the case for genetic algorithms. However, each particle may be moving us towards the a good solution or a bad solution, and that we can determine by using the f function to evaluate. At the end of iteration 1, we basically have updated our vectors. Now we'll start again from the first variable, first particle. We'll use its current position. We'll use the v vector, and particularly for the first particle, to determine the new position by simply fitting in the variable values and the parameter values, and then after determining the velocity, we'll then determine the new position, and after getting the new position we'll check for bounds and we'll update as the steps go accordingly. So that's the we'll do it for the first, for the second particle, third, fourth, fifth particle, and keep on doing it step by step in each iteration until we either reach the end of iterations or the final step is reached. Then we move on to the checking the bounds, then we check the evaluation function, we finally check the after the generation process is complete, we then move on to the updating the population size, and then updating the personal best and global best if certain conditions are met, and so on. So we observed that the new position is not better than the personal best, neither better than the G best, so both of them will not be updated at all, and they'll remain as they are, but we'll update the population as determined in the previous step. Implementation and how the algorithm runs, I think it is interesting to know, or and important as well to know, that changing the value of parameters, the default parameters or the parameters that are there, for example inertia, for example the acceleration coefficients, for example the random numbers, etc. All of these coefficients and random numbers and fixed or default parameters, they do affect the behavior of PSO. In that regard, I'll just talk about the acceleration coefficients in this slide, but I will want to generalize it for all the other parameters as well. For example, let's say that the acceleration coefficients that we have chosen are both 0. That's the first case. In that case, the particles will move in the same direction until it hits the search space boundary, and on reaching the boundary they'll just stay fixed over there. So it's basically, if you put them 0 in the equation for Vi, you will notice that it will basically be only inertia multiplied by Vi, and the rest of and both the other terms that were introduced will be 0. So it will just be inertia, and the current velocity, so the change of direction will never happen. And that is something that these constants, the acceleration coefficients, are going to help you with. So if they are both positive, which is the second case, then particles are independent hill climbers. They'll basically be climbing the hill, and particles will perform local search. So that is the effect of choosing positive coefficients, acceleration coefficients. So if you choose C1 to be 0 and C2 to be positive, then the entire swarm will become one stochastic hill climber, and all particles will get attracted to a single point. Another variation is if you choose C1 equal to C2, then automatically the particle, if both the values are equal, then particle is attracted towards the average of the personal best and the global best for the variable I or particle I. If C1 is very large as compared to C2, then the particles will be attracted towards its P best and will kind of neglect the G best, which is automatically the effect of choosing a very large C1 as compared to C2. On the other hand, if you choose a very large C2 instead of C1, then the particle will be attracted towards the global best and will cause premature convergence towards the optima, and the personal best will not get enough weightage in this case. So if you choose very low values of C1 and C2, then it will produce very smooth particle trajectories and slow movement and proper movement towards the global optima and towards the personal optima as well. And finally, if you choose really high values of C1 and C2, you'll observe very abrupt movements in the algorithm. So keeping this in mind, one observes that the value of C1 and C2 will affect the behavior and how the convergence happens for PSO. So it is absolutely necessary that you take a lot of care when you are designing the parameters and you are selecting the default values for these parameters. So these apparently not so important parameters do play a very important role, and in particular in the behavior of PSO and how you are going to observe the changes visually, as you will probably see later in a couple of minutes. Okay, so now since we are done with the demonstration part as well as the basic working of the algorithm, and we have discussed it in a lot of detail already, so now it's time to discuss the pseudocode. And pseudocode is basically the central nerve of computer science, and for us it's the most important thing. So I'm just going to quickly go through the pseudocode itself, and what you need to realize is I've told you these steps verbally, but now these are written out in form of a pseudocode. So as input, we have got a few variable declarations. We need to define how to calculate fitness of our function given the input vector or possibly a particle. So we need to evaluate its fitness somehow. We need to know the lower bounds and the upper bounds determined by LB and UB respectively. We need to identify that and we need to mention it as input to our function. We need to mention the number of particles that are going to take part in this algorithm. So this is again going to be defined by the user. The number of iterations that we need to run is represented here by T, and this is again going to be input by the user. We need to define the inertia constant W. We need to define the acceleration constant C1 and C2, and this is the overall functional definition or functional requirements for identifying the variables and constants of PSO algorithm. Then we can start running the algorithm. We first need to initialize a random population P and velocity vector V within the bounds. The initial vectors or initial population P would basically be a matrix of size NP multiplied by D, where D is the dimensions or number of variables that you want to optimize, and NP is the number of particles, of course. So the size of the initial population or random population P would be NP cross D. Similarly, for the velocity vector, again the size would be the same. It would be NP cross D as well. After generating the velocity vector and the random population P, We then need to use the evaluation function or the objective function to evaluate the fitness value of the whole population P. Then we need to find the P best and G best vectors. The P best vector is basically P itself, and the f of P best, the functional evaluation of that population P would also be the we'll choose the highest. We'll choose the each fitness value itself as the best fitness value of the population of the individual in the population. And finally, we need to identify the global best value, and for that we'll use f of g best to determine the global or the best the solution with the best global optimal value. With that, once we have generated the initial population, we have generated the random the velocity vectors, we have generated the P best and the G best. You need to understand that the P best that you generate will also be of size NP cross D, since that is the size of P as well, and P best is nothing but P itself. The f of P best would basically be the same as the size of f, which is basically NP cross 1. So it would be the number of particles, and for each particle you'll have one single best fitness value. For the global best, it would basically be the size of 1 cross D. So it would be a single particle, the single particle with the best value, and since there are D variables, so you have got 1 cross D for global best. That's the size of the matrix, and the f of G best is going to be 1 cross 1, since it's the fitness value of this G best value. After you have set the initial parameters and you have set the initial vectors and stuff, you now need to start running the algorithm itself. You start the algorithm by basically, in the outer loop, you have basically started from T from 1 to the number of iterations capital T. Then there's an inner loop where for each particle, so in each iteration you'll update each particle. Each particle is given here, represented here by I. So I is running from 1 to NP. And what do we do inside? Inside there are basically two steps. One is the generation step and the other is the update step. The generation step, in the generation step you need to generate, if you remember, the velocity first of the ith particle. Then you need to generate the new position xi of the ith particle. Then we need to check if the new position was within the bounds. If it is not, we need to correct it. If it is already, we don't need to do anything. Then we need to evaluate the fitness or the objective function value of the ith particle. Then we need to update the population by including the xi and fi. So both the xi and fi have to be updated in any case. Then there is a conditional update on P best and f of P best, and update on conditional update on G best and f of G best if the fitness value of the newly generated function or newly generated position for the particle is better than its personal best or better than the global best. In that case, we'll update the corresponding variable, and we'll continue to do this in each iteration for each particle. So that's the simplest part. The number of particles are given by capital N base P. The steps, if I want to say, if you remember, for generation we had the two equations. The first equation was to determine the velocity Vi of ith particle in a particular iteration, which was given by using the inertia constant and the acceleration constants, represented by Vi here, as you can see on the right side of the slide. Similarly, we could generate the new position xi of ith particle using the equation xi is equal to previous xi plus the velocity that is vector that is just generated, and then the conditions for updating the P best and G best are also given here, and they are the same as we have seen in the earlier slides. So the pseudocode looks very simple and very easy. It is very easy to implement. Yet I think again here the major issue would be how do you convert or formalize the problem. So the formulation of the problem is the main issue as always. So whenever you see a problem, you should try to formulate it quickly into the right format. The right formulation here would be you need to write out how the state is going to be represented for your problem. Then you need to write out what your fitness function would be, what are the lower bounds and upper bounds for each variable, the number of particles that you want to use, the iteration, for example, the number of iterations, the inertia constant and the acceleration constants, and you need to identify, or you need to realize, more than identification, I think you need to realize yourself that what is the effect of each of these constants. What if you choose a very large inertia? What if you choose a very small inertia? What if you choose a very large C1 and a very small C2 or something like that? So those are the things that I've kind of partially mentioned in the previous slide, but you need to realize on your own as well how this particular mechanism works and what is the effect of each of these. So if you have very few iterations, what's the drawback? If you have very large number of iterations, what's the drawback, and so on. So with that, I think you are ready to go and experiment on your own as well as learn PSO, and I hope that you understand the algorithm, you understand the integrity details that I've been talking about, you understand the motivation, and in particular now I think is the right time that you need to go back to the example, try to solve it on your own personally. And secondly, I would really suggest that you go back to the first example of Zakaria and Musa and see that what were although I had simplified it really quite a lot by not including the inertia part and the cognitive part itself, but the social part was the only component in there, and you can see that even with just the social part we could come to a solution in that really simple case. You need to identify that this will never ever happen actually, that you will, or almost never happen, I must say. It might happen of course, but it's very rare that you have got problems as simple as the one we took earlier. Instead it would be more of a 2D or 3D or high dimensional problems where it would be very hard to fit in other optimization algorithms and techniques. That is where I think the PSO fits in the best, and I really hope that you are able to apply this on your own as well to different problems. It can be used for many optimization problems, I think, and the main drawback only, if I have to think about it, would be that although here we are seeing it ran serially, you can always run it in parallel for parallel machines, and if you look at the number of updates that are the serial version of PSO would be really slow, since a lot of computations are done, and you'll kind of require stopping criteria. Mostly it would be the number of iterations or the error bound or something that would help you to converge to a solution rather quickly. So in this slide I'll just show you a quick demonstration about how, and in particular if it is able to find the global optima. The important thing to notice in all these examples is that the particle swarm optimization does give you the optimal value, but it is not guaranteed to converge, as you'll see in a lot of cases. The size of the swarm matters a lot, as well as other parameters as well, and we have probably seen that in the original slide, I think 2 or 3 slides ago, but you'll again see the effect, and you must concentrate on that in this particular example in the video. And finally, I think you'll see that a lot of complex examples will be solved using the power of SOM intelligence, and specifically the PSO algorithm. So enjoy the demo, and I hope you understand how this is implemented and how the overall mechanism works.
This, but in general, we have found the global minima. Then we've got MATLAB's peaks function, something like this, and now we're going to explore this contour with a population size of 2 minima. In some cases, and I think this, so it's a success here. As you can see, it's population size of 40 reached the local global minima, and it has kind of reached there, as you can see. So this is successful. Population size of 45, it will reach much quicker, and here you can see it has converged to the local minima. And population size is an important factor here, as you can clearly see as well in these examples. So moving on to the next slide now. It's not letting me go. Here it goes, and this is the demo.
So let us look at in the demo, and that is I've taken it from the net, and what we see here is that there's a person who has generated some random points, and he wants all the points actually to identify his palm. So this is an application from the image processing part, and in a live video the swarms or the points will try to identify these are generated as you can see. These are set up on the grid, and they'll try to identify the center of the palm, and they've got some objective function also says to them. Maybe it may be the exact distance of the point from the swarm or something, and it's going to use it to converge to a solution and find the center of this person's palm. So just go and view it, and you'll kind of see a very interesting application of swarm particle swarm optimization algorithm. So we finally reached the end of section chain algorithm. Is a simple yet amazingly. Each particle will have two main variables. One is the position, another is the velocity, and it will also have a memory which will be its personal best, and it will have access to the global best position that it can get from other particles. The two main steps in each iteration of PSO is the generation of solutions and updating the personal best and the global best if needed. The algorithm does give optimal values, but is not guaranteed to converge to global optima. The algorithm is more efficient than most optimization algorithms we have seen in the previous lectures, specifically about lecture 6 and 7. 5, 6 and 7. The values of each individual solution is updated in each iteration, so the solution is always going to be updated, but the personal best and global best may or may not be updated depending on the values themselves. And another thing that we have seen in this particular lecture is that if you think that the constants and parameters that have been given in the PSO equation are unimportant, you might have to think or rethink yourself, because they play a very important role in determining the behavior of PSO and how PSO will converge or will not converge. So with that in mind, I wish you all the best for this lecture, and we'll now discuss lecture 7 we'll now discuss applications of swarm and you guys.
Taking it up, it seems to be crossing the 2 hour and 15 minutes mark, so it will count as 4 lectures and not 2 lectures. So that's a good thing about this lecture. So this is the content for week 12 and week 13 for you guys. Make sure you watch the video watch list. So there's a lot of learning in there. In particular, the different lectures and introduction to particle swarm optimization. I've taken a lot of text and context from these anyway. It will help you. Finally, thanks for listening and hope you've learned something during my lectures. Goodbye.